Most people, if you ask them where the edge of the universe is, would say something like 46.5 billion light years away. They would picture a sphere of galaxies, with us at the center and a clean boundary at the edge. They would be confidently wrong. The phrase edge of the universe is hiding at least 3 different boundaries, with 3 different sizes and 3 different meanings. The Hubble sphere, at 14.4 billion light years, the cosmic event horizon, at 16.59, the particle horizon, at 46.5. None of them are equal to each other. None of them are what you would intuitively call an edge. And the deepest of the 3, the one stamped on every cosmology infographic, is not a location at all. It is a wall of light, 2.7 Kelvin, 378,000 years old, surrounding every observer in the universe, in every direction at once. So, what is the wall actually made of? And how can it be around every observer at the same time without being at any specific place in space? Settle in. Hit subscribe if you are new to the channel, because by the end of this, you will know exactly where you are sitting, what is around you, and what is around everyone else. Now, let us gently fall into this. Part 1. The map with a number stamped on it. If you have ever looked at one of those infographics that maps the observable universe, you have seen the number 46.5 billion light years, end to end in any direction. It usually sits stamped in the corner of the diagram, like the scale on a road map, just a quiet little label, promising you that the picture is to scale. A sphere of galaxies, with us at the center, and that number written next to a thin line drawn from the middle to the edge. It is the sort of fact that gets repeated so often, it stops registering as a fact at all. It becomes furniture. You read it, you nod, you move on. But that number is doing something strange in your mind, and you probably have not noticed. When you read 46.5 billion light years, you picture a distance. You picture an edge somewhere out there in the dark, far away, the way you might picture the far side of an ocean. There is here, where you are, and there is out there, where the universe ends. The number is the distance between the two. That is what the diagram is telling you. That is what the scale is for. And that picture is so intuitive, so easy to hold in your mind, that for most people, it is the only picture of the universe they ever carry around. Tonight, very slowly, we are going to take that picture apart. Not because it is useless, it is useful for some purposes, but because it is, in the deepest possible sense, wrong. The number stamped on the corner of that infographic is real. It is well measured. It is one of the most precisely determined quantities in all of physics. But what it actually describes is not what you think it describes. The number is real. The picture that goes with it is not. Here is the first hint, and we are going to start gently. The universe is 13.79 billion years old. We know this with very high precision because the same measurements that give us the 46.5 billion light-year number also give us the age. Now think for a second. If the edge of the universe were 46.5 billion light-years away, then light from that edge would need 46.5 billion years to reach us. But the universe has only existed for 13.79 billion years. The light has not had time to make the trip. It is impossible. And yet there it is, that number, stamped on every map of the cosmos, in every textbook, in every classroom. 46.5 billion light years. So what is going on? Either the number is wrong, or our picture of what it means is wrong. And the number is not wrong. We have measured it from too many directions, with too many independent instruments, against too many cross-checks. The number is solid. It is the picture that is bending. What we are going to do for the next couple of hours is walk our way from the wrong picture to the right one. We will not get there in a single step. The universe does not give up its real shape easily, The right picture is not just a different drawing of the same scene. The right picture changes the very thing you think you are looking at when you look up at the night sky. By the time we are done, the words edge of the universe will not mean what they meant when we started. I want you to hold one image in your mind as we begin. Picture the standard diagram, a sphere of galaxies. You at the center, a line from the center to the surface labeled 46.5 billion light years. A nice, clean geometric shape, the kind you might draw in a high school physics textbook. Hold that image. Notice how comfortable it is. Notice how it makes you feel like you understand where you live. Now I am going to tell you something quietly, and it will mean very little to you right now. But by the end of this video, it will mean almost everything. The edge of the universe is not at the surface of that sphere. The edge of the universe is not even in space the way that diagram suggests. The edge is not where it is when it is, and we will get there. But first we have to take the wrong picture seriously, because that is where most people live, and that is where you live too, probably right at this moment. So let us start with the simple picture. Let us start with the sphere of galaxies and the number stamped on the side, and let us see what happens when we ask a very basic question. Where exactly did that number come from? And what is it actually measuring? The universe began 13.79 billion years ago. Or, more carefully, the part of the universe we can talk about with confidence began then. There was no place where it began. The Big Bang was not an explosion happening somewhere. It was a condition of the entire universe simultaneously. Everywhere was hot, dense, and small. Then it expanded. It is still expanding now. And as it expanded, distances grew. Galaxies that were near each other are now far from each other. Galaxies that we have never moved relative to in any meaningful sense have nevertheless ended up further away from us, because the space between us and them has stretched. This is the central oddness of cosmological distance, and we will return to it. For now, just notice that the standard diagram, the sphere with us at the center, hides this expansion from view. It draws the universe as a static picture, a frozen frame. But the universe is not frozen. It is in motion at every scale. The light arriving at our telescopes tonight has been traveling through a universe that has been getting bigger the entire time. Hold that thought. And hold the wrong picture too, the sphere and the number. We are going to need both, because we are going to spend the next part of this video watching the wrong picture come apart at the seams. Part 2. Why the simple picture fails. Let us try to make the wrong picture work very carefully and see exactly where it breaks. Because the wrong picture is not stupid. It is not lazy. It is a perfectly reasonable picture, the kind you would draw if you had to draw a map of the universe in 5 minutes on a chalkboard. The problem is that the universe is not a chalkboard. It is something stranger. So, a sphere of galaxies. You at the center, the edge 46.5 billion light years away. Universe is 13.79 billion years old. The question is simple. How did the light from the edge get here? Light moves at 1 foot per nanosecond, more or less. That is fast in human terms, slow in cosmic terms. Over the entire history of the universe, light could have travelled, at most, 13.79 billion light years. That is the maximum distance any photon could have covered since the Big Bang. Anything farther than that should be invisible to us. The signal would not have arrived yet. The clock has not had time to tick that many ticks. So why is the diagram drawn with a sphere of radius 46.5 billion light years? Why is that the boundary? The answer is that the diagram is showing two different things at once, and it has not bothered to tell you which is which. The 46.5 billion light years is not the distance the photons travelled. The 46.5 billion light years is the current distance to the material that emitted those photons, and those are not the same number. They are not even close to being the same number, and the gap between them is the first crack in the simple picture. Let me say that again, slowly, because it matters. When you look at the most distant galaxy we can see, the light you are seeing was emitted billions of years ago. While the light was traveling, the universe was expanding. The galaxy that emitted the light was not staying put. The space between us and that galaxy was stretching the whole time. So when the light arrives at our telescope today, the galaxy that emitted it is no longer where it was when it emitted. It is much further away. How much further? Let us pick a real example. The most distant confirmed galaxy as of right now is called JADES-GS-Z14-0. The James Webb Space Telescope spotted it. The light from this galaxy left it when the universe was about 290 million years old. The light has been traveling toward us for about 13.5 billion years. That is the light travel time. That is the number that tells us how long the photons were in transit. But during those 13.5 billion years, space itself was stretching. The distance between us and the galaxy was growing. By the time the light arrived, the galaxy was no longer 290 million light-years away. It was about 33 billion light-years away. The light traveled 13.5 billion light-years. The current distance to the galaxy is 33 billion light-years. These are both correct. They describe the same object. They are not contradictory. They are just measuring different things. Light travel time is one thing. Current proper distance is another thing. Same galaxy, two different numbers, neither one wrong. This is where the simple picture starts to bend. Because if you ask, where is the edge of the observable universe, you have to specify what kind of edge you mean. Do you mean, where was the material that emitted the most distant photons we can see at the moment it emitted them? Or do you mean, where is that material now, after the universe has expanded for 13.79 billion years? These are different questions. They have different answers. And the answers differ by a factor of more than 3. The 46.5 billion light-years stamped on the side of every cosmology diagram is the second number. It is the current proper distance to the material whose photons we are now seeing for the first time. The material is, today, 46.5 billion light-years from us. The photons we are seeing have been in transit for the entire age of the universe. They are old photons from young material, and the material has moved since. Now, here is the part that should bother you, just a little. We do not actually see where the material is now. We see where it was when it emitted the photons. We see a 13.79 billion-year-old snapshot of material that has since been carried by the expansion of space much farther away. We are looking at a memory of the universe, not at the universe as it is. That is true at every scale, by the way. When you look at the sun, you are seeing it as it was 8 minutes ago. When you look at the nearest star, you are seeing it as it was 4 years ago. When you look at the nearest galaxy, in any meaningful sense, you are seeing it as it was 2.5 million years ago. The deeper you look, the older the picture. And at the very deepest you can look, the picture is 13.79 billion years old. The light is just barely getting here. So, what is at the edge? Not material as it is now, material as it was, when the universe was very young. The edge of the observable universe is not a location in space. The edge is a moment in time. The 46.5 billion light-years is the current address of that moment. But the edge itself is not a place. It is an age. This is the first reframe, and it is the gentle one. We have only opened the door a crack. There is more inside. The simple picture also fails for another reason, which we should mention before we move on. The simple picture has a sphere with a clean boundary, just a surface, a wall, as if you could fly there, in some imaginary spaceship, and tap on it. You cannot. There is no boundary in that sense. The 46.5 billion light-years is not where space stops. It is where our view stops. Space goes on past it, maybe forever, probably forever. But our access ends. This is the difference, in plain language, between the universe and the observable universe. The universe is the whole thing, including parts we cannot see. The observable universe is the part of it that has ever sent us light. The number 46.5 billion light-years describes the observable universe, not the universe. The universe could be, and probably is, much larger. There are good reasons, which we will get to think it is infinite. But infinite or not, what we can see is bounded. What is past the boundary is real. It is just not reachable. So we have already opened two cracks in the simple picture. First, the edge of the observable universe is not a place but a moment, and the 46.5 billion light-years is the current distance to the material that produced that moment. Second, the observable universe is not the universe. There is more, on the other side, that we cannot see and possibly never will. We are going to spend the rest of this video making these cracks into doors and walking through them. The picture on the other side is stranger and more beautiful than the simple one. But you need to leave the simple picture behind to get there, so let it go gently. We will not be needing the sphere of galaxies anymore. Part 3. 3 boundaries that everyone confuses. There is a problem we have to clear up before we go any further. The phrase edge of the universe is doing too much work. It is being asked to describe at least 3 different things, and most popular accounts smush them together as if they were the same thing. They are not. They are 3 completely distinct concepts with 3 different definitions, 3 different sizes, and 3 different physical meanings. If you do not separate them carefully, you cannot make sense of any of this. So we are going to slow down and take them one at a time. The first boundary is called the Hubble sphere. The Hubble sphere is defined like this. The universe is expanding. The further away a galaxy is, the faster it is moving away from us. That is just the expansion of space showing up as a velocity. Closer galaxies recede slowly. Distant galaxies recede quickly. At some specific distance, the recession velocity equals the speed of light. That distance is the Hubble sphere. Right now, with the best measurements we have, the Hubble sphere is at about 14.4 billion light-years. Here is what most people get wrong. They hear that beyond the Hubble sphere, galaxies are receding faster than light, and they conclude that no light from beyond it can ever reach us. That is a very natural conclusion. It is also wrong. It is wrong because the recession velocity is not a velocity through space. It is a velocity due to space itself, stretching. A galaxy can recede from us at faster than light and still send us photons that, eventually, reach us. The photons fight against the expansion, slowly losing ground. But because the expansion is not uniform forever, the photons can, in some cases, gain ground over time. Light from beyond the Hubble sphere can reach us, depending on the details of how the expansion changes. So the Hubble sphere is not an edge in the sense that it traps anything inside it. It is a marker of where the expansion rate equals 1, useful for some purposes, not the edge of the observable universe. The second boundary is the particle horizon. The particle horizon is the limit of how far we can see. It is the current distance to the most distant material from which any photon has had time to reach us. This is the 46.5 billion light-years. The particle horizon is the largest of the 3 boundaries, and it is the one usually meant when people say observable universe. The particle horizon includes everything in our past light cone, going all the way back to the beginning. Anything closer than the particle horizon is potentially visible to us in principle. Anything beyond it has never sent us a signal. Now notice the asymmetry. The particle horizon, at 46.5 billion light-years, is larger than the age of the universe times the speed of light, which would be 13.79 billion light-years. That is what we walked through in the last part. The particle horizon is the current distance to material whose light has been traveling for the full age of the universe, and the material has since been carried further away by expansion. The third boundary is the cosmic event horizon. This is the most interesting one, and the one most easily confused with the others. The cosmic event horizon is defined by looking forward, not backward. It asks, if I send a signal today, how far can it possibly reach before the expansion of space carries the destination beyond my ability to ever catch up? The answer, under our current best measurements, is 16.59 billion light-years, plus or minus 0.18. In other words, anything closer than about 16.5 billion light-years right now, you could, in principle, send a signal to. The signal might take billions of years to arrive, but it would arrive. Anything further away than that, even at exactly that current distance, you have already lost. The expansion will carry that destination away faster than your signal can chase it. The light you emit today will never get there. It will fall further and further behind. This is the part that should make you sit up a little. The cosmic event horizon is shrinking in proper distance. As the expansion of the universe accelerates, the maximum reachable distance for any new signal you send shrinks. Galaxies that are inside your reachable range today will be outside it in the future. Once a galaxy crosses your cosmic event horizon, going outward, you have lost it forever. Not because it stopped existing, not because it stopped being visible. It will keep being visible for a while with red-shifted light, but you cannot reach it anymore. Anything you do, today or tomorrow, or in 1,000 years, cannot arrive there. The cosmic event horizon is the real boundary of causal contact. It is the edge of the reachable universe, the universe of things we can, in principle, interact with. And it is smaller than the particle horizon, which is the universe of things we can see, which is itself a different concept from the Hubble sphere, which is where the recession velocity equals c. 3 boundaries, 3 meanings. Hubble sphere at 14.4, cosmic event horizon at 16.59, particle horizon at 46.5. None of them are equal to 13.79, which is the age of the universe times the speed of light. None of them are equal to each other. When somebody says edge of the universe, they almost always mean one of these three, but they almost never say which. And the conversation gets muddled, because if you are picturing the cosmic event horizon and somebody else is picturing the particle horizon, you are not actually discussing the same thing. The cosmic event horizon is about what we can reach. The particle horizon is about what we can see. The Hubble sphere is about where the expansion crosses the speed of light, which sounds dramatic and means almost nothing operationally. For tonight, for the rest of this video, we are going to focus on the particle horizon. That is the boundary of what we can see. That is the boundary at 46.5 billion light-years. And the question we have been building toward is, what is actually at that boundary? What does the surface of the observable universe actually look like if we could resolve it perfectly? What kind of thing is at the edge of seeing? Because the answer is not what you think. Most people, if they think about it for a moment, would say that the edge of the observable universe is a region of very distant galaxies, the oldest galaxies we can detect, the first generation of stars, the cosmic dawn. There is some truth in that, in the sense that the farthest individual galaxies we have spotted with the James Webb Space Telescope are sitting fairly close to the boundary. JADES-GS-Z 14-0 at 33 billion light-years, current proper distance, is one of the most distant individually resolved objects we know about, but it is not at the edge. Even JADES is sitting about 13 billion light-years inside the particle horizon in current proper distance. What is at the edge is something much stranger than a faint galaxy. It is not a galaxy at all. It is not a collection of objects. It is not a region of structured matter. The edge is, in the most precise sense possible, a wall of light. And the wall of light is not made of any individual stars or galaxies. It is the radiation from the moment when the universe first allowed light to travel freely. It is a single moment of cosmic history, frozen and wrapped around us in every direction. That is where we are heading. The next part is where we open the door. Part 4. The actual edge. There is a moment, 378,000 years after the Big Bang, that everything in this video is built around. It is the moment when the universe became transparent. Before that moment, light could not travel. After it, light could travel. And the photons that began their journey at that moment are the photons we see when we look at the edge of the observable universe today. So let us go and look at that moment carefully, because it is the actual edge, and it is not at all what most people imagine when they hear the phrase edge of the universe. Begin in the very early universe. Begin a few minutes after the Big Bang, when the universe is hot and dense and uniform, expanded enough that nucleosynthesis has just finished, the first helium nuclei and the first deuterium nuclei have formed, but everything is still glowing like the inside of a star. The temperature is in the millions of Kelvin. The composition is a soup of protons, helium nuclei, free electrons, photons, neutrinos. The matter is ionized, which is the important thing. Ionized means the electrons are not bound to the nuclei. They are flying around freely in a sea of positively charged ions and negatively charged electrons, a plasma. Plasmas have a particular relationship with light. Light cannot pass through them, or rather, light passes through them very, very poorly. Every photon, on average, travels only a tiny distance before it bumps into a free electron and gets scattered. This process is called Thomson scattering, after Joseph John Thomson, the physicist who first described it in 1906. Thomson scattering is what makes a plasma opaque. Light does not stream through it. Light gets caught, deflected, sent off in a new direction, then caught again, then sent off again, then caught, then sent off, on and on billions and billions of times. The photons do not get anywhere. They just bounce around, trapped, until something changes the medium they are in. For the first 378,000 years, this is what the universe looks like. A bright, opaque, uniform plasma, hot enough to glow, dense enough to scatter light. There are no galaxies. There are no stars. There is no transparent space. The universe is glowing with thermal radiation, but the radiation cannot travel anywhere. It is locked into a perpetual game of pinball with the free electrons. Then something changes. The universe is expanding. As it expands, it cools. The temperature is dropping continuously, and at some point, the temperature drops below the threshold at which electrons can stay bound to protons. The threshold is about 3000 Kelvin. Below that temperature, an electron passing close to a proton will fall into a stable orbit. The two will combine into a neutral hydrogen atom. The proton plus electron, once a free pair, now a single bound atom. Helium nuclei capture electrons too, more slowly, but eventually. This process is called recombination. It is a slightly misleading name because the protons and electrons were never previously combined. They had never been bound together before in the history of the universe. There was no first combination to re, but the name has stuck since the 1960s, and we are not changing it now. Just notice that recombination is the universe doing something it had never done before. It is the first moment that neutral atoms exist in any quantity. The temperature drops below 3000 Kelvin. The free electrons disappear into bound hydrogen and bound helium. The plasma turns into a neutral gas, and the photons, which had been bouncing around in the plasma for hundreds of thousands of years, suddenly have nothing to scatter off. The free electrons are gone. The neutral atoms do not scatter photons in the same way. The universe suddenly is transparent. The transition is not instantaneous. It takes time. The universe does not flip from opaque to transparent in a single moment. The process takes about 115,000 years in light travel time to fully complete. During those 115,000 years, the universe is partially transparent. Some photons are still being scattered, others are streaming freely. But by the time the transition is complete, about 378,000 years after the Big Bang, the universe is essentially transparent. The photons can travel. Now think about what just happened. There is a huge amount of light in the universe at the moment. Recombination completes. The universe has been glowing like the interior of a furnace for the entire previous era. Every cubic centimeter is filled with photons. Now those photons are released. They can finally move. They begin to stream outward in straight lines, in every direction. They have nothing to absorb them, nothing to scatter them. They just travel, and they keep traveling. For 13.79 billion years, they are still traveling now. Some of them, after 13.79 billion years of travel, have finally arrived at our detectors. We see them as the cosmic microwave background. It is the same light. It is just very, very stretched. The light was emitted, originally, at a temperature of about 3000 Kelvin, wavelengths in the visible and infrared, bright orange-red, like the heating element of an electric stove. But for the entire 13.79 billion years it has been travelling, the universe has been expanding. And as space expands, the wavelengths of photons travelling through it get stretched. This is the cosmological redshift. By the time the light arrives at us, it has been stretched by a factor of about 1090. The wavelengths are about 1,000 times longer than they were at emission. The temperature equivalent has dropped from 3000 Kelvin to 2.7 Kelvin. The light has shifted from visible and infrared to microwave. That is what the cosmic microwave background is. It is the light from the moment of recombination, stretched by 13.79 billion years of cosmic expansion. And the surface from which that light comes, the surface of last scattering, is what the particle horizon actually points at. It is what is at the edge of the observable universe. So here is the picture. When you look out at the universe, in any direction, you see galaxies. As you look further, you see fainter and fainter galaxies, increasingly redshifted. At the very faintest, with the James Webb Space Telescope, you see the first galaxies, the cosmic dawn, 200 million to 400 million years after the Big Bang. Beyond that, in older eras, there were no galaxies yet. There was just the dark ages, between recombination and the first stars. We cannot see the dark ages directly with telescopes. They are dark, but in principle, if you could see further still, you would see all the way back to recombination. And there, at 378,000 years after the Big Bang, you would hit a wall. The wall is the moment the universe was last opaque. Before that, light cannot reach you, not because there is no light, but because the light could not propagate. The wall is, in the most literal possible sense, the limit of what light can show you. Notice how this changes the meaning of edge. The edge is not a location in space. The edge is a moment in time. The 46.5 billion light-years is the current proper distance to that moment. But the edge itself is a when, not a where. The wall is not where it is when it is. I want you to sit with that sentence for a moment, because we are going to come back to it later in this video, and it will mean something different by then. The wall is not where it is when it is. For now, just notice the basic geometry. You are inside a sphere of radius 46.5 billion light-years. The surface of the sphere is the surface of last scattering. The surface of last scattering is a wall of light from 378,000 years post-Big Bang. The light has been traveling for 13.79 billion years to reach you. You are at the center. The wall is around you. Around in every direction. There is no spot on the sky that is not on the wall. The wall surrounds you completely. It is a full 4 pi steradians of cosmic boundary. Look up, look down, look left, look right. In every one of those directions, the wall is there, at the same distance, the same temperature, the same age. The wall is not somewhere out there. The wall is, in every direction, all around you. And that is where this video starts to do something to you. Because once you understand that the wall is a moment in time, expressed as a surface in space surrounding you, the question, what is past the edge of the universe, stops making the kind of sense you thought it made. The edge is not a place you could travel to. The edge is a memory. The edge is the first time light could move. And nothing you do, no telescope you build, no signal you send, can reach back and see what was happening before that moment, because before that moment, no signal could escape. The wall is the edge of what light can show. It is not the edge of everything, just the edge of everything light can carry to you. Part 5. The Wall of Light. We have arrived at the wall, so let us go and look at it. Here is what it actually looks like, in the most precise terms we can describe. The wall has a temperature. Today, after 13.79 billion years of cosmological redshift, the wall is at 2.72548 Kelvin. The plus or minus on that number is 0.00057 Kelvin. We know the temperature of the wall to better than 1 part in 5,000. It is one of the most precisely measured quantities in all of physics. The wall is not just at one temperature either. The wall is at that temperature in every direction. If you point a sensitive detector at any patch of sky, anywhere, and measure the microwave background, you get 2.72548 Kelvin. Move to a different patch, same temperature. Move to the opposite side of the sky, same temperature. The wall is uniform, almost. The deviations from uniformity are about 1 part in 100,000. There are tiny, tiny temperature differences from one patch of the wall to another. These differences are the most important data in cosmology. They encode the structure of the early universe, the acoustic oscillations of the photon-baryon plasma, the seeds of all future galaxies. But for the level we are working at right now, just notice the basic fact. The wall is uniform to 1 part in 100,000. There is no other natural surface in the universe that's smooth. The wall has a spectrum. A spectrum is the distribution of light intensity across wavelength. If you measure how bright the cosmic microwave background is at different wavelengths, you get a curve. The curve for the cosmic microwave background is the most perfect blackbody spectrum ever measured in nature. A blackbody spectrum is what an idealized hot object emits if it is in perfect thermal equilibrium with itself. Stars come close, but they have absorption lines and emission lines and atmospheric effects that distort the spectrum. The cosmic microwave background has no atmosphere. It came from a uniform plasma. Its spectrum is, within 50 parts per million, a textbook blackbody at 2.72548 Kelvin. There is nothing else in nature that is this clean. This was first measured precisely by the Cosmic Background Explorer satellite, COBE, in 1990. The COBE FIRES instrument, the Far Infrared Absolute Spectrophotometer, measured the spectrum of the cosmic microwave background and found it to be a blackbody to within the error bars of the instrument. The spectrum is so smooth that any deviation from perfect blackbody would tell us something profound about energy injection in the early universe. There has been no such deviation found. The wall is featureless. In spectrum, the wall has an age. The age of the wall is fixed by when recombination happened, 378,000 years after the Big Bang. The Planck satellite refined this number to a redshift of 1089.80 plus or minus 0.21. Light from the wall has been traveling for 13.79 billion years, minus 378,000. Effectively, 13.79 billion years on the nose. The wall has a thickness. We have been talking about the wall as if it were a perfect mathematical sphere, but it is not. Recombination is not instantaneous. It takes about 115,000 years for the universe to go from fully opaque to fully transparent. During those 115,000 years, the wall is forming. The wall is, in light travel time, about 115,000 years thick. In current proper distance, that is about 30 megaparsecs moving, or roughly 100 million light-years of thickness. Not exactly thin, not exactly a perfect mathematical surface, a shell with finite depth, but against the radius of 46.5 billion light-years, the thickness is negligible. The wall is, for all practical purposes, a sphere. The wall has acoustic peaks. This is the deep structure in the temperature variations. In the photon-baryon plasma before recombination, sound waves were running through the medium. Real sound waves, in the technical sense, pressure, oscillations in the plasma. They had a characteristic speed called the sound speed, which was about half the speed of light in that medium. The waves were driven by the gravitational pull of slight overdensities in the primordial plasma. Each overdensity tried to collapse under gravity, but the photon pressure pushed back, then gravity pulled in again, then pressure pushed out again, oscillating, standing waves on the scale of the universe. When recombination happened, the oscillations were frozen. The photons decoupled from the baryons. The pressure support disappeared, and whatever pattern of oscillation was in place at that exact moment got imprinted on the cosmic microwave background. Different oscillation modes had different angular sizes on our sky today. The largest one, the fundamental, the first acoustic peak, sits at about an angular size of 1 degree on the sky. It corresponds to multipole L equals 220 in the spherical harmonic decomposition of the temperature map. There is a second peak at multipole, roughly 540, a third at about 800, a fourth at about 1100. These peaks are the most exquisite data we have. They tell us the geometry of the universe. They tell us how much ordinary matter there is. They tell us how much dark matter there is. They tell us the expansion rate. They tell us the spectral tilt of the primordial perturbations from inflation. Every one of these numbers comes from fitting peaks to a model, and the fits are extraordinarily good. The wall has polarization. The cosmic microwave background is not just intensity, it is also polarized light. The polarization comes from the Thomson scattering at the wall, which preferentially scatters photons from a quadrupolar distribution of temperatures into specific linear polarization patterns. There are two kinds of polarization patterns: E modes, which look like radial spokes or concentric circles around hot or cold spots, and B modes, which look like a kind of curl pattern, like the eddies of a river. E modes are abundant. They were first detected in 2003 by the WMAP satellite and have since been mapped exquisitely by Planck and ground-based telescopes. B modes are much fainter. They have been detected at the gravitational lensing level, which means we have measured the B modes that are produced when E modes are gently lensed by the matter between us and the wall. But the primordial B modes, the ones produced by inflationary gravitational waves stretching the photons at the moment of last scattering, those have not been detected yet. There is an upper limit. The tensor to scalar ratio, the ratio of primordial gravitational waves to primordial density perturbations, is less than 0.036 at 95% confidence. The next generation of experiments will push this limit down by a factor of 10 or more. If primordial B modes are detected, we will have the first direct evidence of inflationary gravitational waves. The wall has a dipole. Earth is moving through the cosmic microwave background. The motion is the sum of Earth around the Sun around the galactic center, the galaxy through the local group through the local supercluster. All those motions added together give the Earth a velocity of about 370 kilometers per second relative to the cosmic microwave background. The motion shows up as a Doppler shift of the temperature. The direction Earth is moving toward looks slightly hotter by about 3.36 millikelvin. The opposite direction looks slightly cooler by the same amount. This is called the CMB dipole. We subtract it before we do anything else. The dipole is a reminder that the cosmic microwave background defines a kind of preferred frame for the universe. The frame in which the dipole is zero is the frame in which the universe as a whole looks isotropic. Some people, in some online corners, get excited about this and conclude that special relativity must be wrong because there is a preferred frame after all. Special relativity is fine. The CMB rest frame is a fact about the matter distribution of the universe, not a violation of relativity. There is no privileged frame in the relativistic sense. There is just one frame in which the universe looks particularly symmetric. We talked about this in an earlier video. We are not going to relitigate it tonight. Here is what I want you to take from this part of the video. The wall is a real, measured, exquisitely characterized object. It is not an abstraction. It is not a metaphor. It is a sphere of measurable temperature, measurable spectrum, measurable polarization, measurable acoustic structure, measurable thickness. Every property of the wall has been pinned down with extraordinary precision. We know the wall in detail. Scene moment, immersive. I want you to picture, for a moment, what the universe looked like at the instant the wall formed. Imagine the universe at 378,000 years old. Everything is hot, dense, and uniform. A plasma at 3000 Kelvin, the temperature of a dim red dwarf star. The whole universe glows the color of an iron rod in a forge, that deep orange that comes just before red. Every direction you can imagine looking, in this imagined inside view, is the same color, same brightness, same temperature. There are no stars, there are no galaxies, there are no rocks. There is only the glow. Now imagine the moment the universe cools, just slightly, below 3000 Kelvin. The free electrons fall into bound orbits around protons. The fog clears. The light that had been scattering endlessly in a tight game of pinball suddenly has nowhere to scatter. The photons that were bouncing around at every angle, in every direction, all at once start streaming in straight lines. It is not loud. There is no sound to it. Sound waves were running through the plasma a moment ago, but the medium has just changed. Sound does not propagate in the new, transparent universe. The transition is silent and almost instantaneous. The light begins to travel. The photons that were here, at this location in the early universe, head outward in every direction. The photons that were 1 billion light years from here, in the early universe, head outward from their location. Photons from every point in space stream outward from that point. They travel through the universe, which is still expanding, but which is now transparent enough to let them pass. For 115,000 years, the universe continues to clear up. The last few free electrons get captured. The last few stray photons stop scattering. Then the wall is done forming. The universe is transparent. The photons keep traveling for 100 million years, for 1 billion years, for 10 billion years, for 13.79 billion years. And then a few of them, arriving from a tiny patch of sky that you could not even pick out without an instrument, hit the detector of a microwave telescope on a planet in the third arm of a barred spiral galaxy in a small group of galaxies orbiting in a supercluster on the outer shell of one of the largest matter filaments in the observable universe. The telescope reads the temperature, 2.72548 Kelvin, with error bars, to better than 1 part in 5,000. That is the wall. That is what is at the edge of the observable universe. That is the surface of last scattering. The wall is the edge of what light can show. Notice that sentence. It is going to come back. Part 6. The wall is around you. I want you to do something with me. I want you to imagine extending a sphere outward from where you are sitting in every direction, slowly, smoothly, evenly. The sphere has you at its center. The radius is going to grow. Start at 1 foot. The sphere is the size of a basketball, more or less. It includes the air immediately around you. The interior is small enough that you could reach out and touch the boundary. Almost trivial. Grow it to 10 feet. The sphere now includes most of the room you are in. The walls of the room are still outside the sphere, probably. The room itself is partially inside, partially outside. You are at the center. Grow it to 100 feet. The sphere is the size of a small building. It includes the room, the next room over, the floor below, the floor above. People in nearby rooms are inside your sphere now. Grow it to 1 mile. The sphere is a large city block. Cars, trees, sidewalks, the building you are in, plus a few neighbors. You are still at the center. Grow it to 10 miles. The sphere now covers a small city. Highways, neighborhoods, parks. The local airspace. Grow it to 1,000 miles. The sphere covers a region of a continent. The lights of distant cities are inside your sphere. The curvature of the Earth is becoming noticeable, but the sphere is still much smaller than the planet. Grow it to the size of the Earth. The sphere now contains the entire planet. Every person, every plant, every ocean, every mountain, every photon emitted by any human flashlight on the surface of the Earth in the last fraction of a second. Keep going, past the Earth, past the Moon. The sphere is now 400,000 kilometers in radius. The Moon is inside. The Earth is inside. The space between them is inside. Past the Sun. The sphere is 150 million kilometers in radius. The Sun is inside. The Earth is inside. The entire inner solar system is inside. Past Pluto, 5 billion kilometers in radius. The whole solar system is inside, past the heliopause, past the Oort cloud, at the very edge of where the Sun's gravitational influence still organizes orbits. The sphere now has a radius of about 1 light year. We crossed an entire light year of distance, just adding zeros, past the nearest star, 4.24 light years away. Proxima Centauri. The sphere passes through Proxima and keeps growing. Past the nearest dozen stars, past the local interstellar neighborhood, past the local arm of the Milky Way. The sphere is now several hundred light years in radius. Thousands of stars are inside. Most of them are red dwarfs, dim and small. A few are bright giants, nebulae, star-forming regions. Past the center of the Milky Way galaxy, the sphere now has a radius of about 25,000 light years. Sagittarius A star, the supermassive black hole at the galactic center, is inside the sphere. So is the central bulge of the galaxy, with its dense population of old stars, past the edge of the Milky Way disk, about 50,000 light years from the galactic center. The sphere now covers the entire Milky Way galaxy, 200 billion stars or so. The entire disk, past Andromeda, 2.5 million light-years away. The sphere now contains the entire local group of galaxies. Milky Way, Andromeda, Triangulum, a few dozen dwarfs and satellites. The local group is what will eventually merge into a single elliptical galaxy in the deep future, past the Virgo cluster. 54 million light-years. The sphere now contains the local supercluster of galaxies. Thousands of galaxies, organized into a network of filaments and voids, past the Coma cluster, the Hercules cluster, the Shapley concentration, past the Great Wall of Galaxies. The sphere is now hundreds of millions of light-years in radius. Millions of galaxies are inside, past 1 billion light-years. The sphere now contains millions and millions of galaxies, organized into the large-scale structure of the universe, the cosmic web, the filaments, the walls, the voids. Past 5 billion light-years. The sphere now contains a substantial fraction of all visible galaxies in the universe. The light from the most distant galaxies inside the sphere is from when the universe was only about 8 billion years old, past 10 billion light-years, past 20. The sphere is now into the deep universe. The galaxies inside the sphere are increasingly young, increasingly redshifted, increasingly different from the galaxies we live among, past 30 billion light-years. The sphere now includes the most distant individual galaxies we have observed with the James Webb Space Telescope, JADES-GS-Z14-0, and a few others at similar redshifts. Past 40 billion light-years, past 46 billion light-years, and finally, at 46.5 billion light-years, the sphere stops growing. Or, more precisely, the sphere does not stop growing, but it stops finding new things. Past 46.5 billion light-years, the sphere reaches the wall, the surface of last scattering, the cosmic microwave background, the first photons that ever crossed open space. Beyond that, there are no photons that can reach the center of the sphere. There is no light past the wall. You are still at the center. The sphere is around you. It is 46.5 billion light-years in radius. The surface of the sphere is the wall, the cosmic microwave background, the surface of last scattering. The wall has a temperature of 2.72548 Kelvin. The wall is uniform to 1 part in 100,000. The wall is the same in every direction. The Wargweiser. Emotional anchor existential. Now, here is the part where the picture changes you. When you look up at the night sky, in any direction, you are looking at the wall. The wall is in the constellation of Orion. The wall is in the constellation of the Big Dipper. The wall is in the patch of sky directly behind your head, the patch you cannot see because your head is in the way. The wall is in the floor underneath you, all around you, in every direction your senses can imagine looking. The wall is not far away in some abstract sense. The wall is around you, right now. It is 2.7 Kelvin in your kitchen ceiling. It is 2.7 Kelvin in the floor underneath your feet. The microwave photons from the surface of last scattering are passing through your body, dozens of them per second, every direction, every angle. You have been inside the wall your entire life. You will be inside the wall every moment of your remaining life. Every cell of your body has been bathed in microwave photons from the early universe since the moment you were conceived. The wall is not a distant object. The wall is a wraparound surface that surrounds every observer in every direction in the universe. You are at the center of your own sphere. Hold that. The wall is around you. It is, in the most literal possible sense, the boundary of everything you can ever see. It is not a place you could travel to. It is not even a region of space that you could in principle reach. The wall is the moment 378,000 years after the Big Bang, expressed as a current spatial boundary surrounding you. You sit at the center. The wall surrounds you. It always has. It always will. This is the second reframe, and it is the one that does something to your sense of where you live. You do not live in a universe that has an edge somewhere far away. You live inside a sphere whose surface is a moment in time, wrapping around you in 4 pi steradians. You are at the center of your sphere. Every observer, anywhere, is at the center of their own sphere. There is no privileged center. There is also no edge in any other meaningful sense. There is only your sphere and everyone else's sphere, and they are all the same kind of sphere, and they all surround the observer who lives at the middle of them. This is the universe you live in. This is what the night sky actually is. The dark patches between the stars are not empty. They are the wall, redshifted, faint, but real. Every direction you can look, the wall is there. The wall is the edge of what light can show, and it is everywhere you turn. Part 7. The wall in detail. Now that we have established what the wall is and where it sits, we can spend some time looking at it the way a cosmologist looks at it. The wall is not just a featureless sphere of microwave glow. It has structure, faint structure, almost vanishingly faint, but structure all the same. And the structure of the wall is the most complete portrait we have of the universe in its infancy. Let me give you the basic data first, and then we will unpack what it means. The cosmic microwave background has a mean temperature of 2.72548 Kelvin. Subtract the dipole, which is the Doppler shift from Earth's motion at 370 kilometers per second, relative to the cosmic rest frame, and what you have left is a wall whose temperature varies from place to place by about 30 microkelvin peak to peak. 30 millionths of a degree, against a background of nearly 3 degrees. The ratio is 1 part in 100,000. That is the order of magnitude of the temperature anisotropies of the wall. If you have ever seen one of those colourful oval maps of the cosmic microwave background, the kind that shows red and blue patches scattered across the sky, you have seen the temperature anisotropies. The red patches are hotter than average by tens of microkelvin. The blue patches are cooler than average by the same amount. The patches range in size from about a degree across down to fractions of a degree. The patterns look random, but they are not. They encode the structure of the early universe. Here is what is producing the patterns. In the photon baryon plasma, before recombination, slight overdensities and underdensities in the matter distribution were oscillating. Real sound waves, in the strictest sense of the word. Sound waves are pressure oscillations in a medium, and the early universe had a medium with pressure. The photons provided the pressure. The matter, the baryons, provided the inertia. Sound waves propagating through this medium had a characteristic speed, the speed of sound in the photon baryon plasma, which was about 1/3 times the speed of light. About 57% of the speed of light. Fast. The waves were driven by gravity. Slight overdensities of matter in the early universe attracted more matter gravitationally. The matter would fall in. The photons, coupled to the matter through Thomson scattering, would also try to fall in. But the photon pressure resisted compression. As the matter compressed, the photon pressure pushed back. The infall would stop, then reverse. The matter would bounce outward. The pressure would relax, then gravity would pull it back in again, oscillating, standing waves on the scale of the universe. Different overdensities had different sizes. Small overdensities oscillated quickly. Large overdensities oscillated slowly. The sound waves had time to oscillate a different number of times in the 378,000 years between the Big Bang and recombination. Waves of a particular characteristic size had time to complete exactly 1/2 oscillation in that interval. Waves of half that size had time to complete exactly 1 full oscillation. Waves of 1/3 the size completed 1.5, and so on. Each ratio of size produced a different peak of intensity in the final pattern of the cosmic microwave background. This is what the acoustic peaks are. They are the standing wave pattern of sound waves in the early universe, frozen at the moment of recombination, when the photons decoupled from the matter and the pressure support went away. The pattern of the standing waves got imprinted on the cosmic microwave background. We see it today as the multipole spectrum of the temperature anisotropies. The first acoustic peak sits at multipole L equals about 220, corresponding to an angular size on the sky of about 1 degree. The first peak is what we call the fundamental. Waves at this scale had time to complete exactly 1/2 oscillation between the Big Bang and recombination. The peak is the largest feature in the cosmic microwave background power spectrum, and its angular position is what tells us that the universe is spatially flat. If the universe were positively curved, the peak would appear at a larger angular size. If the universe were negatively curved, it would appear at a smaller angular size. It appears at 1 degree. The universe is flat to within 0.5%. The second peak sits at multipole L equals about 540. The third at about 800. The fourth at about 1,100. Each peak has a different physical meaning. The first peak constrains the geometry of the universe. The second peak, especially in ratio to the first, constrains how much ordinary matter there is. The third peak constrains how much dark matter there is. Higher peaks constrain damping scales and the spectral tilt of the primordial perturbations from inflation. When you put all the peaks together with all the modern data from the Planck satellite, you get a stunning fit to a model with just 6 parameters. 6 numbers describe the entire cosmic microwave background to a precision of better than 1%. Those 6 numbers are the age of the universe, the Hubble constant, the density of ordinary matter, the density of dark matter, the optical depth to reionization, and the spectral tilt of the primordial perturbations. 6 parameters, that is it. Every wiggle in the cosmic microwave background power spectrum can be predicted from those 6 numbers, plus the standard equations of cosmology. This is one of the most successful applications of physics to nature in the entire history of science. We have a wall of light from 378,000 years after the Big Bang. We measure its temperature variations across the sky. We extract a power spectrum from the variations. We fit a 6-parameter model to the power spectrum. The fit is essentially perfect, to within the precision of the measurements. 6 numbers describe the early universe completely, given the right framework. Now, let me complicate that picture slightly. The 6-parameter model is called lambda CDM. Lambda is the cosmological constant, the dark energy. CDM is cold, dark matter. The model fits the cosmic microwave background beautifully. It also fits a lot of other data beautifully, but it does not fit all the data. There are tensions between the cosmic microwave background and other measurements. We mentioned the Hubble tension earlier, where the Planck satellite gives an expansion rate of 67.4 kilometers per second per megaparsec, and the local distance ladder gives 73. That tension is now over 5 sigma. Either one measurement is wrong, or there is new physics that nobody has identified yet. The cosmic microwave background, by itself, fits lambda CDM perfectly, but the cosmic microwave background plus other things does not. Let us also talk about polarization. The cosmic microwave background is not just intensity, it is polarized. The polarization comes from Thomson scattering at the wall. When the universe was reionizing, photons were scattering off free electrons, and the scattering preferentially aligned the polarization of the photons depending on the local quadrupole pattern of the temperature. If the temperature in a small region of the plasma was hot in one direction and cold in the perpendicular direction, photons scattering through that region would acquire a specific polarization. There are 2 kinds of polarization patterns. E-modes look like radial spokes around hot or cold spots, or like concentric circles. They are the dominant polarization pattern, and they have been measured exquisitely by WMAP, Planck, and ground-based experiments like ACT and SPT. E-modes confirm what we already knew from the temperature anisotropies. They add additional cross-checks on the model. They constrain the optical depth to reionization more tightly. B-modes are different. They look like curl patterns, like little eddies of polarization. There are 2 sources of B-modes. The first is gravitational lensing. The E-modes from the wall pass through the matter between us and the wall, and the matter gently lenses the photons. Lensing converts a small fraction of the E modes into B modes. We have measured lensing B modes. They are real. They tell us about the matter distribution at intermediate redshift. The second source of B modes is more interesting. Primordial gravitational waves from inflation, if they exist, would stretch and squeeze the photons at the moment of last scattering and produce B modes directly at the wall. These primordial B modes have not been detected. Current bound is R less than 0.036 at 95% confidence, where R is the tensor to scalar ratio. If primordial B modes are detected at any future level, it will be the first direct evidence of inflationary gravitational waves. We will have seen a signal from the inflation era, which ended about 10 to the negative 32 seconds after the Big Bang. The wall we currently see is at 378,000 years. Inflation is much, much earlier. Gravitational waves from inflation would penetrate the wall and arrive at our detectors today. There are several experiments working on this. BICEP Array, Simon's Observatory, CMB-S4, Lightbird, a satellite mission. If any of them detect primordial B modes at the predicted level, the entire program of inflationary cosmology will get a direct experimental confirmation. We will be reading a signal from past the wall. Now I want to step back and look at all of this from a slightly different angle. The wall is not just a sphere of microwaves. The wall is the most heavily characterized object in cosmology. It has been measured at multiple frequencies, with multiple instruments, in space and on the ground, by independent teams. Every parameter we extract from the wall matches every other parameter to within the error bars. The cosmic microwave background is a vast, self-consistent dataset. It tells a single story about the early universe. The story it tells is that the universe at 378,000 years was a nearly uniform plasma, with tiny density fluctuations of order 1 part in 100,000. The fluctuations were the seeds of all later structure. Where there was a slight overdensity, gravity pulled in more matter over the subsequent billions of years, and a galaxy eventually formed. Where there was a slight underdensity, the region remained empty and grew into one of the great voids of the cosmic web. The universe we live in, with all its galaxies and clusters and filaments, started as 1 part in 100,000 variations in temperature on the wall. Everything we see today, every star, every planet, every grain of sand, every conscious thought, every life that has ever lived, traces back to those tiny variations. The wall is not just where the photons come from. The wall is the seed of everything. If the temperature in your patch of the wall, 13.79 billion years ago, had been 1 part in 100,000 colder, the matter in your patch might not have collapsed into a galaxy. The sun might not have formed. You might not be here. The fluctuations of the wall are the origin story of every solid thing. This is a very strange thought to sit with. The wall is around you. You have been inside it your entire life. And the wall, in some indirect but real sense, is what made you. You are a downstream consequence of the temperature variations of a sphere of microwaves that has been wrapping around you since you were born. The wall is the edge of what light can show. It is also the edge of what made you possible. Part 8. The wall is not perfect. Let me show you something that should not exist. In 2004, a team of cosmologists named Patricio Vielva and his collaborators were looking at the cosmic microwave background data from the Wilkinson Microwave Anisotropy probe. They were applying a technique called spherical wavelet analysis, which is a way of finding patches of the sky that have temperature distributions that look different from the surrounding regions. They ran the analysis, and they found something. In the constellation Eridanus, At galactic coordinates of about 208 degrees longitude and minus 56 degrees latitude, there is a region of the cosmic microwave background that is colder than it should be. The region is about 5 degrees across, which is about the size of a fist held at arm's length. The temperature deficit in the region is about 70 microkelvin below the mean. At the deepest point, the deficit is closer to 150 microkelvin. The patch was given a name, the CMB cold spot. Now, 70 microkelvin sounds like a small number, and it is. The total range of the temperature anisotropies is, after all, only about 30 microkelvin peak to peak in the small-scale features. But the cold spot is large, 5 degrees across. At that angular scale, the standard cosmological model predicts variations of only a few microkelvin. 70 is much more than the model expects. The probability of finding a region this cold, this large, in a random realization of the standard model is somewhere between 1 in 1,000 and 1 in 100, depending on the methodology used. It is significant. It is not extreme, but it is significant. The cold spot has been confirmed by subsequent observations. Planck saw it. Ground-based experiments saw it. It is a real feature of the wall, not an artifact. The question is, what is it? The conventional explanation is the Eridanus supervoid. In 2015, Istvan Sapudi and his colleagues at the University of Hawaii reported that the region of sky containing the cold spot also contains an unusually large void of galaxies between us and the wall. The void is about 1.8 billion light-years across, centered at about 3 billion light-years from us. The void contains far fewer galaxies than the average region of the universe at the same distance. It is genuinely empty relative to the cosmic mean. Voids of galaxies can affect the cosmic microwave background through something called the late integrated Sachs-Wolf effect. The Sachs-Wolf effect is a small perturbation to the temperature of cosmic microwave background photons as they travel through gravitational potentials. When a photon enters a gravitational well, it gains a small amount of energy. When it leaves, it loses an equal amount. In a static universe, the gains and losses would exactly cancel, but the universe is not static. It is expanding, and the expansion is accelerating. In a region of underdensity, like a void, the gravitational well is shallow. As the universe expands, the well gets shallower over time. A photon entering the void gains less energy than it loses on exit. The photon emerges from the void slightly colder than it entered. Many photons crossing the void come out cold. The patch of sky behind the void appears cold. The Eridanus supervoid provides part of the cooling we see in the cold spot. It does not provide all of it. The supervoid accounts for somewhere between half and 3/4 of the temperature deficit, depending on the exact properties of the void and the exact model used. The remaining quarter to half is unexplained by conventional physics. Now we get to the interesting part. There is a hypothesis, published, peer-reviewed, not refuted, that the cold spot is the imprint of another universe brushing against ours. The hypothesis was first published by Laura Mersini-Houghton, a cosmologist at the University of North Carolina, in a series of papers from 2006 through 2008. The basic idea is rooted in eternal inflation. In eternal inflation, our universe is one of many bubble universes nucleating from an exponentially expanding parent vacuum. The bubbles can, in principle, collide with each other. If a collision happened in our cosmic past, the collision would leave a specific kind of mark on the cosmic microwave background, a roughly circular cold or hot patch with a specific size and shape depending on the details of the collision and how long ago it happened. Mersini-Houghton calculated what the expected signature would look like and compared it to the observed cold spot. The fit is not perfect, but it is not impossible either. The cold spot has the right general size. It has the right general kind of asymmetry. It sits in a region of sky that could be consistent with the predictions of a particular collision geometry. The hypothesis is consistent with the data. Consistency is not confirmation. Other hypotheses are also consistent. In 2011, a group of cosmologists named Stephen Feeney, Matthew Johnson, Daniel Mortlock, and Hiranya Paris ran the first systematic observational test for bubble collision signatures in the WMAP 7-year data. They looked for the specific pattern of features that the eternal inflation models predict. They did not find any features that exceeded the noise threshold. The Planck data, when it became available, was added to the analysis. Still no signal above noise. The eternal inflation bubble collision hypothesis is not refuted, but it is not confirmed either. The cold spot is consistent with a bubble collision. It is also consistent with an exotic statistical fluke. It is also consistent with the supervoid, plus some unmodeled effect we have not identified. Scene moment immersive. I want you to picture this. A patch of sky in the constellation Eridanus, 5 degrees across, about the size of your closed fist held at arm's length. Most of the night sky, when you look at it through a sensitive microwave telescope, has a uniform glow of 2.7 Kelvin, modulated by tiny temperature variations of a few tens of microkelvin. This patch is different. This patch is cold, not by much. 70 microkelvin colder than the average, but cold in a way that the standard model does not quite predict. Imagine zooming into that patch. Through the lensing dust of our galaxy, through the network of intergalactic gas, through the great voids and walls of the cosmic web, eventually you reach the surface of last scattering in that direction. The wall is there, just like everywhere else. It glows at 2.72548 Kelvin, minus 70 microkelvin or so. About 1 part in 40,000 colder than the average. Why colder? Maybe because a vast region of underdensity sits between us and the wall in that direction, and the photons crossing it have lost energy. That accounts for maybe half of the cooling. Maybe more. The remaining cooling is something else. Maybe it is an exotic statistical fluctuation that happens once in every 1,000 random realizations of the standard model, and we got the realization with the cold spot. Maybe it is a feature of the wall itself. Maybe the wall, at that one patch, was already colder by some amount when it formed, because something happened to the early universe in that direction that did not happen in others. And there is one specific possibility that nobody has been able to rule out yet. The cooling in that patch might be the literal, physical bruise left on our universe by another universe that brushed against us billions of years before the wall existed. 2 bubbles in eternal inflation, expanding from neighboring points in the parent vacuum, touching once at the moment of contact, then separating forever. The point of contact would leave a mark on the wall. When the wall eventually formed, we would see the mark as a circular cold patch in the cosmic microwave background. If that is what we are seeing, then the cold spot is the only direct evidence we have, anywhere, that another universe exists. The wall has a bruise. The bruise might be where something past the wall touched us once. We do not know if that is the right interpretation. The other interpretations are also alive. We probably will not know in our lifetimes. The signal is too small, the alternative explanations too plausible, the available data too limited. But this is the kind of thing the wall lets us see. Even with all of its smoothness, even with all of its uniformity, the wall is not perfect. It has bruises, and one of the bruises might be a window to a universe that is not ours. There are other anomalies in the wall. The northern and southern ecliptic hemispheres show slightly different amounts of large-scale temperature variation. The asymmetry is small, about 3 sigma, but it has persisted across multiple data releases from WMAP and Planck. The quadrupole and octopole moments, the 2 largest scale temperature variations on the wall, are aligned with each other and with the ecliptic plane. The alignment has a chance probability of about 1 in 1,000 under the Standard Model. People call this the axis of evil, half in jest, half in seriousness. None of these anomalies is, by itself, definitive. Any one of them could be a statistical fluke. Several of them could be statistical flukes. But there are enough of them, of various kinds, that the question of whether the Standard Model fully describes the wall remains technically open. The mainstream view is that they are all statistical accidents. The minority view is that they hint at physics we have not yet identified. For the purposes of tonight, the point is just this: the wall is not perfectly smooth. It has features that the Standard Model does not fully account for. Some of those features might be evidence of something past the wall. We are still working it out. Part 9. The walls past the wall. We have been talking this entire video about the wall as if it were the wall, the single boundary, the unique edge, and in one sense it is. The cosmic microwave background is the only wall we can currently see directly with photons. It is the only wall that has actually been mapped, but it is not the only wall there is. Or rather, it is not the only wall there ever was. There are at least 2 other walls in the early universe, and a third one that might exist. Each of them is older than the cosmic microwave background. Each of them, if we could see it directly, would push the horizon of what we can observe deeper into the early universe. Each of them is, in principle, accessible to us, with the right kind of detectors. We have not yet built the detectors, but the walls are there. They are real. They are radiating signals at us right now. Let me name them in order of how old they are and how close they are to the Big Bang. The first wall is the cosmic microwave background. We have covered it 378,000 years after the Big Bang. The wall of photons, the one we know. The second wall is the cosmic neutrino background. The cosmic neutrino background formed when the universe was about 1 second old. Before that, neutrinos were tightly coupled to the rest of the matter through weak interactions. After that, the universe had expanded and cooled enough that neutrinos could stream freely. They have been streaming ever since. They are everywhere. There are, on average, 336 neutrinos per cubic centimetre, at a temperature today of about 1.95 Kelvin. 2 billion of them are passing through your body every second. We have indirect evidence that the cosmic neutrino background exists. Its presence affects the expansion rate of the early universe, which affects the cosmic microwave background. The cosmic microwave background data is consistent with 3 light neutrino species, which is what the Standard Model of particle physics predicts. The number is called n effective, and the Planck measurement gives n effective equals 3.04 plus or minus 0.18, which is exactly consistent with 3. Good evidence of 3 flavors, not direct detection of the background photons, but evidence. We have not directly detected the cosmic neutrino background. Direct detection is fiendishly difficult, because neutrinos at 1.95 Kelvin have extraordinarily low energies, and their interaction cross-sections with ordinary matter are tiny. There is an experimental program called Ptolemy, based on tritium beta decay, that aims to detect the background. The end point of tritium beta decay is sensitive to whether neutrinos are absorbed by tritium nuclei from the background flux. If Ptolemy ever runs at full sensitivity, it might detect the cosmic neutrino background directly. That has not happened yet. If we ever detect the neutrino background directly, the horizon of what we can observe moves backward. We currently see the universe at 378,000 years through the cosmic microwave background. With direct neutrino detection, we would see the universe at 1 second. The volume of the observable universe, expressed in light travel time, would expand to encompass everything after the first second. Almost all of cosmic history would be in principle accessible to us. The third wall is the primordial gravitational wave background. Gravitational waves decouple from everything else extremely early. There is no interaction in the universe that can effectively scatter a gravitational wave. Gravitons interact so weakly with matter that, in practice, no detector can stop one. The only way to make a gravitational wave is to make a mass move in a particular asymmetric way. The only way to detect one is to measure the resulting strain in spacetime as the wave passes through your detector. The primordial gravitational wave background was generated in the standard picture during inflation about 10 to the negative 32 seconds after the Big Bang. Quantum fluctuations of the inflaton field were stretched to macroscopic scales, and they sourced gravitational waves of a wide range of wavelengths. After inflation ended, those gravitational waves have been propagating freely. They are still here. They are passing through you right now, although their amplitude is extraordinarily small. We have not directly detected the primordial gravitational wave background. We have detected gravitational waves from astrophysical sources like binary black hole mergers and binary neutron star mergers. The Laser Interferometer Gravitational Wave Observatory, LIGO, has been doing this since 2015. But the primordial background is a different beast, much lower amplitude, much broader frequency range. We do not have the sensitivity yet. The most promising way to detect the primordial gravitational wave background in the short term is indirectly through B-mode polarization of the cosmic microwave background. The primordial gravitational waves passing through the wall at the moment of last scattering would have stretched and squeezed the photons in specific ways, producing curl-like polarization patterns. If we can measure those patterns at the predicted amplitude, we have detected the primordial gravitational wave background through its imprint on the wall. This has not been done. The current upper bound on the tensor to scalar ratio is r less than 0.036 at 95% confidence from the BICEP and Keck array experiments. The next generation of experiments, like the BICEP array, Simon's Observatory, CMB-S4, and Lightbird, will push the bound by a factor of 10 or more. If primordial B-modes exist at the level predicted by simple models of inflation, they will be detected within the next decade or so. If we detect them, we have done something remarkable. We have, in effect, seen past the wall. The cosmic microwave background tells us about the universe at 378,000 years. The B-modes from inflation tell us about the universe at 10 to the negative 32 seconds, 34 orders of magnitude in time. We would have a direct probe of the inflationary era. Now think about what this means. The wall is not where it is. It is when it is. We have been saying that since part 4. The wall is a moment in time expressed as a spatial boundary, and the moment is 378,000 years. But the cosmic microwave background is not the only moment. The cosmic neutrino background is a wall too. Its moment is 1 second after the Big Bang. If we could see it directly, we would have a different wall at a different distance, marking a different moment. The primordial gravitational wave background, if we could see it directly, would be another wall at another distance, marking yet another moment, even closer to the beginning. The walls are a sequence. Each one is older than the last. Each one is closer to the Big Bang. The cosmic microwave background is the wall of last scattering of photons. The cosmic neutrino background is the wall of last scattering of neutrinos. The primordial gravitational wave background is the wall after which gravitational waves decoupled. What lies past each wall? Past the photon wall, the universe at 1 second old. A hot, dense plasma of nucleons, electrons, photons, neutrinos. Smaller than it is now by a factor of about 1 billion. Hotter than it is now by the same factor. Past the neutrino wall, the universe in its first second, quarks, gluons, maybe a quark-gluon plasma. The temperature is in the millions of trillions of degrees. The composition is becoming exotic. We can model it. We can run particle physics experiments at energies that approximate it. The LHC at CERN reaches energies corresponding to about 10 to the negative 12 seconds after the Big Bang. We have indirect access to that era, past the gravitational wave wall, the universe during inflation. The temperature here is not a meaningful concept. The matter content is not the matter content of today. The inflaton field, whatever it is the dominant degree of freedom. Space is expanding exponentially. Quantum fluctuations of the field are being stretched to macroscopic scales. We do not know what is past the gravitational wave wall in any direct sense, but we have models. Past the gravitational wave wall, eventually, we run out of models. We get to the quantum gravity era, where the energy scale is so high that the standard model and general relativity stop being adequate descriptions. We need a theory of quantum gravity to go any further. We do not have one yet. So here is the updated picture. The wall we see, the cosmic microwave background, is one wall in a sequence. The walls are arranged in time. Each one is closer to the Big Bang than the last. The cosmic microwave background is the most accessible because photons are easy to detect. The neutrino wall is harder. The gravitational wave wall is harder still. And past the gravitational wave wall, we run out of physics. There is a wall we cannot see past, not because the medium was opaque, but because our theories stop working. The wall is not where it is when it is. And it is one of several walls, each at a different when, each closer to the beginning. We have seen one of them. We are working on seeing the others. The edge of what light can show is just the edge of one particular kind of seeing. The edge of what anything can show, ever, is a different and deeper question, and we have not answered it yet. Part 10. What is past the wall? We have been treating the wall throughout this video as a kind of boundary, something beyond which we cannot see, and that is correct. But the wall is not a boundary of the universe. It is a boundary of our seeing. There is more universe past the wall. We just cannot see it with photons. So what is past the wall exactly? The standard answer, and it is a confident answer for most of the journey backward, is more of the same. The wall is at 378,000 years after the Big Bang. Past the wall, going backward in time, you have the opaque plasma. Before the opaque plasma, the universe was even hotter and denser, and the composition was different. Going back, you eventually hit the era of nucleosynthesis, between about 1 second and 3 minutes after the Big Bang, where the first nuclei formed: hydrogen, helium, traces of lithium. The relative abundances of these elements, which we can measure today, give us our other major cosmological constraint, in addition to the cosmic microwave background. The Big Bang nucleosynthesis prediction and the observed abundances agree to within about 10% across the range from primordial deuterium to primordial helium-4. It is an extraordinarily strong test. Before nucleosynthesis, going further back, the universe was hot enough that nuclei could not form. The temperature was above several billion Kelvin. Quarks and gluons were the relevant degrees of freedom, in addition to leptons and photons. The standard model of particle physics describes this era. We can test it at colliders. We have not run a collider at the temperatures of the very early universe, but we can extrapolate. Before about 10 to the negative 12 seconds, the universe was hotter than anything we can produce in a laboratory. Past that point, our extrapolations get less reliable. We are using theory more and data less. But the theory is good enough that we have specific predictions for what was happening. Symmetry-breaking events. Phase transitions. The decoupling of the strong nuclear force from the electroweak force. The decoupling of the electromagnetic force from the weak force. These events happened, in the standard picture, in the first picoseconds after the Big Bang. Before all of that, before any of the standard model symmetry breakings, was the inflationary era. Inflation, if it happened, was a brief phase of exponential expansion that lasted some incredibly small fraction of a second. The exact timing depends on the model. Most simple models put the inflationary era at around 10 to the negative 32 seconds. During inflation, the universe expanded by at least a factor of 10 to the 26 in something like 10 to the negative 34 seconds. That number is so large that comparing it to anything in human experience is meaningless. The universe grew a lot, very fast. What drove inflation? The hypothesis is that there was a field, the inflaton, that had a very specific kind of potential energy. The field was sitting at a high point in the potential, slowly rolling down. While it was rolling down, the energy of the field was dominating the universe, and the energy of a slowly rolling scalar field has a specific equation of state that produces exponential expansion. When the field finally reached the bottom of its potential, inflation ended. The energy of the field converted into the standard model particles. The universe became radiation-dominated, and the standard hot Big Bang story took over. This is what is past the photon wall, in the simple picture, the pre-recombination plasma, the nucleosynthesis era, the standard model era, the inflationary era. And before inflation, we get to a region where our theories stop being adequate. The energy scales become so high that quantum gravity matters. We do not have a theory of quantum gravity. We have proposals: string theory, loop quantum gravity, various others. None of them is established. None of them has been confirmed experimentally. So past the inflationary era, going backward, we run out of physics. We hit the edge of theory. There is, in the strict sense, no consensus on what happened before inflation. There are guesses, there are interesting mathematical models, there is not knowledge. Now, I want to add one more layer to this. Inflation, if it is correct, makes a strong prediction about what is past the photon wall in the spatial sense, not the temporal sense. The inflationary models predict that the universe is much larger than the observable universe, probably much, much larger. The volume increase during inflation is so enormous that whatever finite region we live in today is just a tiny patch of a much larger inflationary domain. In some models of inflation, the inflationary era never globally ends. Regions of the inflating universe continue to inflate forever. Other regions, like ours, exit inflation and become standard expanding universes. In these models, our universe is one bubble in an effectively infinite multiverse of bubble universes, all nucleating from a common parent inflating vacuum. Each bubble universe could have different physical constants, potentially. The multiverse picture is speculative, but not crazy. It follows from straightforward extrapolations of inflationary models that fit the cosmic microwave background data exquisitely. So what is past the wall, spatially? More universe. In our same bubble, the universe is at least 251 times larger than the observable universe in volume, with 99% confidence, based on the curvature constraints from the cosmic microwave background. That is the conservative bound. More aggressive inflationary models predict the universe is 10 to the 23rd times larger. Some predict it is infinite. We do not know the exact size. We know it is at least very large. We know it is, in standard models, much larger than what we can see. Past our bubble universe, in some inflationary models, there are other bubble universes. We cannot reach them. The space between bubbles is inflating faster than light can cross it. The bubbles are causally isolated from each other. We cannot communicate. We cannot observe them. Except, possibly, for one thing, we talked about it in the previous part. If two bubbles collided in our cosmic past, the collision would leave an imprint on the cosmic microwave background. The cold spot might be one such imprint, or it might not be. The data is consistent. The data is not conclusive. This is what is past the photon wall, the early universe, the inflationary era, possibly other bubble universes, possibly other physics, possibly an infinite expanse of more universe of the same kind we live in. The wall is not the boundary of everything. It is just the boundary of what photons can show us. There is much more behind it. The wall is the edge of what light can show. It is not the edge of what exists. It is not even the edge of what we have indirect access to. The cosmic microwave background, the nucleosynthesis abundances, the inflationary B-mode signature, the eventually detectable neutrino background, the eventually detectable gravitational wave background, all of these together let us probe past the wall, in ways the wall itself cannot directly show. The wall is the edge of one specific kind of access. It is not the edge of everything, but it is, for now, the most striking edge we have. The wall is what is at 46.5 billion light-years. The wall is what photographs of the cosmic microwave background actually show. The wall is what is in the red-shifted glow of every patch of dark sky between the stars. The wall is the closest thing the universe has to a single defining boundary that any observer can point at. The wall is what is at the edge of seeing. Part 11. Other observers and their walls. There is one more reframe in this video, and it is the strangest one. So far we have talked about the wall as if it were one wall, as if the cosmic microwave background were a single coherent surface that any observer in the universe would see in roughly the same way. That is not true. The wall is not one wall. It is many walls. There is one wall per observer, and no two walls are exactly the same. Let me unpack this. The wall we see is the surface from which photons travelled for 13.79 billion years to reach us. The material at the surface, today, is 46.5 billion light-years away. But that material is in a specific place, not a generic place. It is, in current proper distance, sitting on a spherical shell of radius 46.5 billion light-years, centered on Earth. Now consider a different observer. Imagine a being on a planet around a star in a galaxy that is, from our perspective, 30 billion light-years away. That galaxy is well inside our observable universe. We can see it. The James Webb Space Telescope might even resolve it as a faint dot at high redshift. Their galaxy is at 30 billion light-years from us, in current proper distance. From their perspective, they are sitting on a planet around a star, in their galaxy, and they are at the center of their own observable universe. They look around, and they see galaxies at varying distances. They look further, and they see the most distant galaxies in their universe. And further still, they see their wall, the cosmic microwave background, as it appears in their sky. Their wall has the same temperature as our wall, 2.72548 Kelvin. To within their measurement precision, their wall has the same age, 378,000 years after the Big Bang. Their wall has the same statistical properties as our wall, the same acoustic peaks, the same temperature anisotropies, the same polarization patterns. Statistically, the walls look like they were drawn from the same distribution, because they were. The early universe was, in the standard picture, statistically uniform, but their wall is not in the same place as our wall. The material that makes up their wall is the material that was emitting photons 13.79 billion years ago that the observer in question is now receiving. That material is sitting on a spherical shell of radius 46.5 billion light-years, centered on them, not on us. How much do our two walls overlap? Geometrically, you can work it out. Our wall is a sphere of radius 46.5 Gly, centered on Earth. Their wall is a sphere of radius 46.5 Gly, centered on a galaxy 30 Gly from Earth. The two spheres intersect because 30 is less than 93, which is twice 46.5. The intersection is a circle. Two spherical shells, both of radius 46.5 gli, with centers 30 gli apart, intersect in a circle. Most of our wall is not part of their wall. Most of their wall is not part of ours. The walls partially overlap, but they are mostly different walls. The intersection circle is where they agree about what the wall is. Now generalize this. Pick an observer anywhere in the universe. Each observer has a wall. Each observer's wall is a sphere of radius 46.5 billion light-years centered on them. Each observer's wall is at the same temperature, the same age, the same statistical properties as ours. Each observer's wall is made of the material that, 13.79 billion years ago, was emitting photons that traveled for the age of the universe and arrived at the observer's location. There is no global wall. There are local walls. There is one wall per observer. The walls partially overlap, mostly do not. Each observer sits at the center of their own sphere. Each observer is at the center of their own observable universe. And no observer has any particular claim to being the cosmic center. There is no center. There are just observer-centered spheres, one per observer, each describing a different volume of the universe, each surrounding its observer with the same temperature, the same age, the same kind of wall. Scene moment immersive. Now imagine the different observer in detail. They are, let us say, a thinking being on a planet around a star in a galaxy that is 30 billion light-years from us in current proper distance. They live in a galaxy that has spiral arms not so different from the Milky Way. They have a sun, which to them is just the local star. They have a sky full of nearby stars and distant galaxies. They might have astronomers. They might have built telescopes. Their sky has a cosmic microwave background. They have measured it. They have found that it has a temperature of 2.72548 Kelvin. They have measured its anisotropies. They have found acoustic peaks at the same multipoles as us. They have detected E-mode polarization. They are searching for primordial B-modes. They have run their analysis. They have their own version of the lambda CDM model. The values of the cosmological parameters they have measured are, to within their precision, the same as the values we have measured. They think their wall is in their sky in every direction. They are right. They sit at the center of a sphere of radius 46.5 gli. The sphere is the same kind of sphere as ours. It surrounds them. It is the limit of what they can see with photons. They have looked up at their sky, and they have seen the same uniform glow we see. They have concluded, correctly, that they live in an old universe that was hot and dense once, and that the wall in their sky is the surface of last scattering for their observable universe. But here is what is strange. Most of the material that makes up their wall, today, is not material that makes up our wall. We share a thin sliver of wall, where the two spheres of radius 46.5 gli intersect. The intersection is a circle, about the size of 46.5 gli across, with most of each wall outside the intersection. Most of their wall is in regions of the universe we will never see. Most of our wall is in regions of the universe they will never see. We agree on the statistical character of the wall. We disagree on which patches of the early universe we are looking at. This is true for every observer. Every observer sees a wall. Every observer's wall is locally complete, in every direction. Every observer's wall is in the same kind of place, the same kind of moment, the same statistical structure, and no two observers' walls are made of the same material. Emotional anchor, existential. Here is what that does to the picture. You are at the center of your own sphere. We said this back in part 6, when we extended the imaginary sphere outward from your location until it touched the wall. You are at the center. The wall is around you. Every observer is at the center of their sphere. Every wall is around its observer. There is no global wall. There is no universal edge. There is no single boundary of the observable universe in the cosmic sense. There are local walls, one per observer, each describing a different patch of the early universe, all of them statistically equivalent. This is, in a quiet way, the deepest reframe of all. The edge of the universe is not a property of the universe. It is a property of where you are looking from. Every observer makes their own edge by the simple act of being at a location. Your edge is yours. Some other observer's edge is theirs. There is no edge that exists independent of being looked at. You sit at the center of your own sphere. Everyone, everywhere, sits at the center of their own sphere. The spheres are real. The walls are real. The temperatures are real. The acoustic peaks are real. But there is no global geometry that designates any one sphere as the right one. There is only your sphere, and theirs, and someone else's, and so on, and they are all the same kind of sphere, and they all look identical from the inside. This is what the wall actually is. It is not the edge of the universe. It is the edge of one observer's universe. The universe, as a whole, has no such single edge. The universe is, in the simplest model, the entire region containing all of these observer-centered spheres, plus everything past all of them, which is mostly inaccessible from anywhere. You have been inside your sphere your entire life. You will be inside your sphere your entire remaining life. You will never escape your sphere, in the sense of getting to a place where the wall is in a different direction or at a different distance. The wall moves with you. Walk a mile. The wall is still around you, the same distance away in every direction. Take a spaceship to a star 10 light years away. The wall is still around you, the same distance away in every direction, almost exactly the same patches of the early universe as before, because 10 light years is nothing on a scale of billions. Travel 10 billion light years. Now the patches of the early universe making up your wall are different. But the wall is still around you, the same age, the same temperature, the same statistical structure. You cannot leave your wall. You cannot look past your wall. You can only stand at the center every moment of your life and notice that it is there. Part 12. The wall fades. We have one more thing to say, and it is the most quietly disturbing thing in this entire video. We have established that the wall is around you, that the wall is a moment in time, expressed as a spatial boundary, that the wall is one of several walls in the early universe, that the wall is local to each observer, and there is no global edge. All of that is true now. All of that has been true for billions of years. All of that will continue to be true for some time to come. But the wall will not last forever. The wall is a temporary feature of cosmic history. There is a future in which the wall is, in any practical sense, gone. And in that future, anyone looking at the sky will see no wall, no Big Bang, no evidence of cosmic expansion, no history. The wall is the edge of what light can show. And what light can show is finite in time, even though the wall has been there for 13.79 billion years and will be there for hundreds of billions more. Here is what happens. The universe is expanding. The expansion is accelerating. We have known this since 1998. The cause of the acceleration is dark energy, or possibly something more complicated, but the observational fact of the acceleration is now well established. The Hubble sphere, at 14.4 Gli today, is roughly constant in proper distance, under accelerating expansion, but the cosmic event horizon shrinks. The horizon of what we can reach is closing, and as the horizon closes, the visibility of distant objects fades. The cosmic microwave background does not escape this fate. The photons of the cosmic microwave background, the wall itself, are still being received by Earth every second in the form of microwave radiation at 2.72548 Kelvin. The wall is bright in microwaves. It is the dominant background radiation in the microwave part of the spectrum. But the wall is being redshifted. As the universe continues to expand, the wavelengths of the cosmic microwave background photons we are receiving today get longer. The temperature equivalent of the wall drops. Today, it is 2.7 Kelvin. In 1 billion years, it will be about 2.1 Kelvin. In 10 billion years, about 1.1 Kelvin. In 100 billion years, about 1/10 of a Kelvin. In 1 trillion years, the temperature equivalent of the cosmic microwave background will be on the order of millikelvin or below. The redshift, if accelerating expansion continues at the current rate, accumulates exponentially. The wall fades. There is a temperature below which the wall is no longer detectable by any practical instrument. We do not know exactly where that limit is, but it is somewhere around 1 trillion years from now, give or take a few orders of magnitude. After that, no civilization, no matter how advanced, will be able to detect the cosmic microwave background. The wall will still be there, in principle. The photons will still be arriving at any detector that can resolve their unimaginably long wavelengths and unimaginably low intensity. But the wall will be below the noise floor of any reasonable measurement. The wall, for practical purposes, will be gone. Scene moment immersive. Imagine a civilization 1 trillion years from now on a planet around a long-lived star in a galaxy that has merged with several neighbors into a single elliptical cluster. The local group, in our era, will have merged into a single elliptical, sometimes called Milkomeda, on a timescale of a few billion years. That elliptical will continue to evolve over the next few 100 billion years, occasionally merging with stray dwarfs. Eventually, it will settle into a stable, old elliptical galaxy. Stars in that galaxy will continue to form, very slowly, from the dwindling supply of gas. There will still be a sun, somewhere, on which a planet, somewhere, might harbour life. That life, if it builds telescopes, will look at the night sky. What will they see? They will see their own galaxy, full of stars, in the usual patterns of an elliptical. They will not see the rich structure of disk and arms and dust lanes that the Milky Way had in our era. The elliptical is smoother, the stars are older. They will not see other galaxies. Or rather, they will not see any of the galaxies that, in our era, fill the sky beyond the local group. All of those galaxies will, by 1 trillion years from now, have receded past the cosmic event horizon. The light they emitted, billions of years before our era, has been redshifted to wavelengths too long to detect. There is no Andromeda in their sky, because Andromeda merged with the Milky Way long ago. There is no Virgo cluster, no Coma cluster, no large-scale structure. The cosmic web is invisible. The galaxies are gone. They will not see the cosmic microwave background. The photons that, in our era, give a glow of 2.7 Kelvin in every direction will, in their era, be at a temperature equivalent below their detection threshold. The wall is still around them, in principle. The wall is still there, but the wall is invisible. Imagine astronomers in that civilization trying to do cosmology. They have a galaxy. They have stars. They have a long history of careful observations. They build the best telescopes they can. They observe the sky for 10,000 years. They build models. They write papers. They try to figure out where they came from. They conclude, honestly and rigorously, based on the data available to them, that the universe is static. There is no evidence of expansion. The galaxies they can see are all in their own elliptical, and the stellar motions within it do not show the kind of recession that would suggest cosmic expansion. There is no microwave background to tell them about a hot, dense past. There are no distant galaxies to tell them about the depth of cosmic time. They look at the sky and they see a static, eternal universe. They would be wrong. We know they would be wrong because we have the data they will not have. We know the universe started 13.79 billion years ago, that it has been expanding ever since, that the expansion is accelerating, that the cosmic microwave background pervades everything. The civilization in 1 trillion years will not have access to any of this. The evidence will have faded. The wall will have receded past detection. Emotional anchor, existential. Here is what that does. We live in the era when the wall is visible. We live in the era when the cosmic microwave background can be measured. We live in the era when galaxies still recede from us at observable rates. We live in the era when the Big Bang is empirically detectable. This will not always be true. There is a future in which the wall is gone and the evidence of cosmic origins is unrecoverable. We are inside the wall. We are also inside the brief window of cosmic history in which the wall can be read. This is not a fact about the universe. It is a fact about us and our place in cosmic time. We are early. We are in the era when the cosmic record is open. The civilization, 1 trillion years from now, will not be in that era. They will live in a universe that looks static, that looks eternal, that looks free of any evidence of a beginning. They will be wrong. But they will be honestly wrong because the evidence will have receded past their ability to detect. Be grateful that you can see the wall. Be grateful that you live now, when the cosmic microwave background still bathes the sky in microwaves. Be grateful that the photons from 378,000 years after the Big Bang are still arriving at telescopes and at the surfaces of every object in the universe, including your body. Be grateful that the wall is still around you, because the wall is the edge of what light can show. And we said that earlier in this video, when we were just establishing what the wall is. The wall is the edge of what light can show. But there is one more turn to that sentence, the one we have come back to now. The wall is the edge of what light can show, and light cannot show forever. The wall is the edge of seeing, and seeing is finite. The wall fades, the evidence fades. The cosmic record closes. The universe, in the deep future, becomes unreadable. The story of where we came from becomes literally invisible. The wall, the most coherent fact about cosmic history we will ever know, fades into a featureless dark, and the universe, in that future, looks exactly like what the simple wrong picture said it was. A static, eternal background, with no Big Bang, no expansion, no edge, no wall. The wall is around you tonight. Tonight is a kind of cosmic privilege. We live in the era when the wall is visible. We live in the era when the edge is readable. We live in the era when the cosmic microwave background can still be measured, when the Big Bang is still detectable, when the surface of last scattering is still there for any sufficiently sensitive instrument to see. Look up at the sky. The wall is in every direction. The wall is 2.7 Kelvin. The wall is 378,000 years after the Big Bang. The wall is around you. You are at the center of your own sphere. You are inside the wall. You always have been. And, for the brief window of cosmic history in which you exist, the wall is still visible. The edge of what light can show is still there. The wall has not faded yet. We are in the era when it can be read. We are in the era when the universe is still telling us where it came from. Sit with that. Hold it. Let it settle. The edge of the universe is stranger than you can imagine. It is a wall of light. It is a moment in time. It is around you in every direction. It is yours alone, in a sense, and shared with everyone, in another sense. It will fade. It is here now. You are inside it. You always have been. The wall is the edge of what light can show, and tonight, light can still show it.